Okay, thank you.
I'm happy to be here, so please ask questions whenever anything is not clear. So I'd rather move slowly than move fast and leave lots of things unexplained. I have to briefly mention what I didn't finish last time, because there's a couple of caveats you have to be aware of. So we ended up with that expression, and from which I really fast gave you that this converges to Brownian, the white noise, and this converges to the delta function, everything, which is true almost. So first of all, I didn't compute you the coefficients, and I believe the coefficient would be like that. Now, the trick, there is a little caveat. First of all, this indeed goes to a delta function, right? It's a periodic delta function, so if you write it correctly, it will be, how do you call it, not a brush, somehow. There's a special term. Yeah, a comb, yeah, a delta comb. So they're all located with certain frequency, and you see if you want the frequency go to 0 to make the interval of periodicity go to infinity, you want your omega naught to be sent to 0. So, which basically omega naught sent to infinity, that is, which basically means that the mass goes to 0. So there's a mass separation between the big mass and the small mass, because this would be, and one would be the heaviest of the small masses. So there is, of course, this, if you want to recover on the entire time interval a periodic behavior, a sort of decay of correlation function, then you need to send mass to 0, masses of small particles. Now, the next comment is that, you see, we indeed recover the white noise. So this would converge to W dot T. If we had summation from 0, because to get the complete orthonormal basis, you need, well, k equals 0 as well, which gives you a constant for the cosine. Sine disappears, but cosine has a constant. But of course, k is equal to 0 gives you some weird stuff here. So in reality, what happens, since you have a periodic system, you don't have a Brownian motion, you have what's called the Brownian bridge. So you basically remove the 0th Fourier mode, so the Brownian motion becomes periodic, and that's called the Brownian bridge. So it connects 0 with the end. So this white noise is white noise, but it's not a derivative of Brownian motion, it's a derivative of Brownian bridge. So, and that little addition is probably only relevant to mathematicians. For physicists, it might not mean much. Everything is fine, except, so you'll go next reduction as, so k goes to, well, I actually have sum to infinity already, get minus kappa over m. Now, here is another caveat, so we have to be careful. This does converge to a delta function, but it converges to a half of delta function in a way, because you're integrating from 0 to t, and if you're not careful enough, which at some point I was computing things, and of course I wasn't careful enough, just put a delta function, so you have a bunch of oscillating things, right, which converge to a delta function when you take the summation, but you're only integrating this part. So there will be 1/2. If you don't have that 1/2, you completely destroy your proper distribution in the end. So this will be 1/2 here, and then we'll have P of t, I think, kappa over m, and then I'll get this coefficient, pi over omega naught. And then these guys will give me plus square root of kappa pi, beta omega naught, W dot T. Plus, there will be actually extra terms, because in order to get the real Brownian motion, I'll have to add the 0th mode, which will also give something. So I'll just write this Brownian bridge corrections. Yeah, this 1/2, if you now treat this as a stochastic differential equation, it's so-called Ornstein-Uhlenbeck process, to which you can compute the invariant measure. And of course, it's going to be the invariant measure for P will be proportional to e to minus P squared over 2m, and there'll be beta. So, and I think so omega naught is fine. So now, if there is no these two, there's no these two. These two is related to this, and so you won't get the correct expected invariant measure. So why this is important? Because sometimes people just jump to this kind of Markovian approximation in the general framework and forget that there is 1/2, and then get incorrect results in simulations, for example, because things slightly different. Okay, so I'll stop here with this specific example, and I'll start doing the general formalism. Any questions regarding this anymore? Okay, good.
What is the name of this process?
Ornstein-Uhlenbeck, so it's called. Hopefully I don't misspell it. Ornstein. Yeah, in physics it's known as Langevin equation, right? So it's in mathematics it's known as Ornstein-Uhlenbeck process, which.
In finance, because I think it's important in finance as well.
Well, finance, basically math finance came from sort of canonical mathematical notation, plus their own stuff, of course, but yeah. Okay, so why did we manage to do what we managed to do? Of course, because everything was linear. So there's no way we could have solved all those things in nonlinear case. And thus, okay, so somehow I'm confusing things. It should go up. It should go further up. Okay. So we want to develop similar formalism, which would allow us to make this kind of reduction for even nonlinear systems. So suppose we have notation is going to get crazier and crazier, and please interrupt me if there's anything you misunderstand. So suppose we start with Hamiltonian equations. Q dot is equal to dH dp. P dot is equal to minus dH dq. Or you can think in general, more general case, simply x dot is equal to f of x. Right, so x will collectively refer to p's and q's, which are generalized momenta and coordinates in my Hamiltonian formulation. So, if you have this equation, it is a nonlinear equation, so none of what we did would work. So we want to get a linear equation. So how do we get a linear equation? So these x's and p's and q's, they describe the microscopic state of our system. If we want to have an observable in classical formulation, it's a function on the phase space, right? So x, say pq, belongs to, I'll just write it, a phase space. And then observables are functions. On the phase space. Right, so we can take f of x. So now on this space of observables, of course, we introduce evolution. F of x and t is equal to f of x of t. Right, so if we start from, we'll write like this, x of t such that x of 0 is equal to x naught. That would be more precise. So this creates an evolution, right? So this creates, well, better say induces. So induced evolution on a function space over the phase space. And that obeys a linear equation. So that's why we go from phase space dynamics to function space dynamics, because we get linear equations and we can play the tricks with our with the same kind of variation of constants formula. So what is the dynamics on the function space? Well, that's the so-called Liouville equation, right? If we look at this definition and we simply differentiate, right, use the, how's it called, chain rule, we'll get d f dt x naught t will be what? Will be the gradient of f with respect to x naught, right? Well, so gradient n of x at t times x dot. And that's, yes.
Sorry, I'll wait, continue.
Yeah. And that is, well, f of x
You need
here.
a total derivative? You need
Hmm?
a total derivative?
Well, there's a little ambiguity, right? So I'm supposed to be using different letters here because, strictly speaking, these are different functions, right? This is my original function on the space of x alone, and this is a different function. So when I take a partial derivative of this thing, it's the same as taking total derivative of this thing.
Okay.
So it's see, because the derivative with respect to time goes through total derivative of this, and then I go further. So x dot. So we'll have this, right? So grad f. So I'll write it like this again, and then I'll have f of x.
So just to comment, the usual Liouville equation has the opposite sign because it describes the evolution of densities rather than
Yeah.
totals.
So that is true. So that's so we can go to the Hamiltonian equation. So what happens is that so we can call this L acting on F. So what happens is that in Hamiltonian formulation there is no difference between the two, because well, except for the minus sign, because the phase flow is preserved, so the phase volume is preserved. In other words, divergence of F is equal to 0. So let me write down equations for the Hamiltonian case, right? Or so let's write it maybe. So we'll get F grad acting on F. So we'll call this Liouville equation as well, but generally speaking, so we can have an evolution equation for the density. And there's slightly different versions of the projection operator formalism. One could be worked out for these variables, one could be worked out for those variables, and this is basically the difference between Swansea approach and Mori approach, if I understand correctly. So evolution for density will be, well, let's write it also t is minus rho. So, okay, I'm answering this question, I'm running ahead of myself a little bit. So what is this rho? You see, I have f of x, and I'm evolving a function here. On the other hand, I can always say that my f of x and t is simply integral of my original f of x with rho of x and t. Right, dx.
So it's going to be conditional on an initial.
Yeah, conditional on initial. Yeah,
Yeah,
I have to
yeah.
condition on initial condition. So x of naught is equal to x naught. Yeah. Something like this. So, yeah, it doesn't make sense, right? So rho of x naught is given. But only because I'm starting from some distribution. So,
Ibrahim, if you go back, in the third line from the bottom at the end, that gradient is with respect to what then, after you make that change?
this would be
No, it's the third line.
it's initial condition. So this function depends only on the initial condition.
Yeah, exactly.
So there's nothing. So you should put here x naught.
And that's true at the end of the third to last line as well. That gradient is with respect to x naught.
Which line?
The third to last line.
Two lines up from where you're writing.
here, here, here.
All those gradients.
No, not that one. Well,
This
the
one?
next one, that one.
Yeah, I mean,
Yeah.
there is only x naught here, so it depends
Right.
on the initial condition and time. So when I write the gradient, it's the gradient with its x variable, if you want.
Should use two letters.
Yeah, sorry?
If you get from left to right,
You
that's what
should
he's asking.
use two letters.
I should use the same f, yeah.
This is terribly confusing.
Shall we change it? Okay, let's
Let's
let's call this.
Change it, then you'll get confused later on.
Yeah. I'll,
Yeah.
so if we put here tilde or something, we'll have the original f here, and then after this original f here, I'll get back to tilde. So it will be
Yeah, yeah.
Small f.
small f.
Oh, we have small.
It's my function which governs the evolution of the dynamical system. In case of Hamiltonian system, it's just dh dp, dh dq vector of these variables. Anyway, so I'm diverging a little bit. So the point is that you can get evolution equation for the density of states. If you start from some initial distribution, you can get the yeah, this will actually be x is equal to conditional on x is equal to x naught. I mean, if you want to have expected value here, then you do it with the initial distribution. So you can basically obtain this operator by integrating by parts this operator. And if you have proper boundary conditions, then that's what you get. So it's again, in Hamiltonian dynamics, this is usually what's called Liouville equation. But of course, if you do it, you'll get minus f grand draw, and this is 0 if phase volume is preserved. Phase volume is preserved, which is the case in Hamiltonian dynamics. So but basically these two things differ just by sign.
Perhaps it's worth saying before you go back to your original derivation that there's a nice paper by Nordholm and Swansig which goes through the projection operator formalism in both representations. And for us physicists, it draws a nice analogy with the Heisenberg and Schrödinger representations in quantum mechanics, which makes everything look very familiar. And it's a similar story here. The time evolution is, conjugate.
Yeah, so I should make a little comment here. Also that in physics, usually they don't look at this operator. So what they do, they write it df dt is equal to I, f, to make it a sort of formal analogy of the, where L tilde is of course just minus IL, or wherever you want to put your minus to. So in this case, this will formally look like a Schrödinger operator, and you can carry out classical and quantum mechanical formalism in general exactly in the same way. But from a mathematical standpoint, it's just manipulation of symbols. So instead of having my L, like here, it would be Hermitian. I'll just say it's anti-Hermitian. And my inner products are all real, so I'm not dealing with any complex variables here. Doesn't make sense. Okay. So initial point for us will basically be this equation. It's a linear equation. It's an equation in some function space, so we'll just use the same variation of constants formula on this equation as we were using on the linear equation and see what happens. Now we can safely erase this. Again, so the final goal is to sort of decompose the entire evolution, then the entire dynamics into parts which correspond to dynamics of interesting things and dynamics which is the evolution of non-interesting things. So we'll start with this, right? So given a function, given some function on the phase space, we have evolution equation. Well, I'm gonna cheat even more. I'm gonna switch this back to full derivative, and I'll explain you why. So f dot of x and t is equal L f of x and t, and f of x and 0 is equal to my f of x. So this is my initial condition. And this kind of transitioning between what is a function and what is a sort of vector in a certain function space is a bit subtle, it's tricky. Even after you think about it for a week, you can still get confused once in a while. So this is initial condition. So in principle, there is any arbitrary function. There's just, you can call it hg, and this is where you start with. You start with f of x. Now, why do I put here a dot? I consider this as just an ODE in a proper function space. Well, it is a partial derivative if you look at it as a bunch of values in just Rn, right? So in your phase space. But if you think of this as a derivative in a function space, you just have the same values of x, right? And then you move front in time. So this gives you evolution of your function. So this is nothing else as an ODE in a function space, which is a partial differential equation, if you want. So generally speaking. So we want to work with this guy now. Okay, of course, L has to be properly specified. I mean, you cannot just write that it's a Laplacian or something or some transport operator, because you need boundary conditions and such things, so which I'll of course all skip, so it will take too long to describe all those things. So formal solution so f of x and t is e to power lt. No, that's f of x. That's right. We just take an exponential operator of that one, and here, of course, that's what I said. So you need boundary conditions and all those things, because clearly, if you have Laplacian, say, depending on boundary conditions, you'll have entirely different, say, values for e to lt. Okay, let's try to convert this equation into something that looks like what we did for the for equation, well, in the previous example, last time. We'll have f dot of x and t is equal to L. Let's put in some p and q here. Well, actually, no, let's not put that here yet. Let's write it first like this: e to power lt f of x, and then L here, right? And then we can write this like this: e to power lt L f of x, and then I'll write it as e to power lt plus q f of x. I'm always confused. Maybe I should have done it the first way. That's why once, yeah, I think it's good. So yeah, I need to. No, I want my L on the other side, because it's a bit tricky, right? Depending where you put your L and P and Q, you will have slightly different expressions, and only one of them is good. Yes, let me put L here actually. Well, so far it's just formal manipulation, right? I've simply substituted expression for f of x and t in terms of the propagator. Then I commuted them, which I can do. Then I simply inserted p plus q, and my p plus q right now are some operators such that they're equal to identity. So in this particular case, there is no, for this step, there is no difference what p's and q's are. A bit later, we'll choose them as some projection operators, and thus the projection operator formula. Okay? So, now we get f dot of x and t is equal to, well, let's pull out the first part, e to the power lt. PL f of x, and then we'll have plus e to the power lt QL f of x. Okay, now this is something that we'll keep as a function which we like, right? So we'll choose p, choose it to be a projection operator on the space of stuff we like, interesting quantities. So in this case, here we're projecting the dynamics on a particular space of the variables that we care about. So this will give us the term which only depends on the variables that we care about. Now the rest will be there, so we'll treat with it. We'll deal with it in a second. So let's think about this. How can we do it?
Interesting does not have to be slow at this stage.
No, at this stage nothing has to be slow. So the slowness and fastness, it comes very late in the game. It's when you try to do some approximations. So what do you do here? There's many ways to do it. Generally speaking, so equation x dot equals to f of x should allow, for example, for an invariant measure. Well, let's assume it has a density. It doesn't have to, so generally, but in physically interesting situations, it's good to have one. So we'll call it rho equilibrium of x. So what does it mean invariant measure? It means that our Liouville equation, the proper one, the minus f rho equilibrium is equal to 0. Right? That's the invariant measure. Now, if you have this invariant measure, you can generate an L2 space, a Hilbert space where you take products of functions, inner products, with respect to this invariant measure. So this is the scene. So this rho equilibrium generates L2 space. In which sense we take any f of x, g of x, and I'll use a notation common in physics, average fg, which is simply integral f of x, g of x, rho equilibrium of x dx, or whatever my Rn. So this does not have to be a RAND. It can itself be infinite dimensional space, but generally speaking, that's right. So this is what we call equilibrium averages. So when we average something with respect to this measure, we'll just refer to this thing as equilibrium averages. This may or may not be Gibbs measure or microcanonical. I think Swansea originally used microcanonical, actually in the original 6.2. So Swansea's paper on this, I think, was 61 something, and then Morris was 65. And Swansea used more formulation where he would propagate the density function of select variables, and then Morris would use equation where he'd propagate the variables themselves.
Can you just write those names?
Hmm?
Can you write those names you mentioned?
Yes. So the entire thing. So is let me. I should have written it long ago, right? Because that's what I'm doing. So that's the name. Okay, so this generates an O2 product, and in this O2 space we can have projections. So as soon as you have a space within a product, you can have orthogonal projections with respect to that inner product. So what are we going to do? We'll take, let me proceed here. So we select a subspace. H, subspace of my L2. This will be the quantities that I care about. So they will all live in this subspace. And then set P will be orthogonal projection. On this subspace.
Orthogonal is equilibrium with the scale.
Yeah, orthogonal meaning it is orthogonal with respect to the scalar product, which I defined here. Now, here is a relation of this to a condition of expectation. So, suppose, use a different color. Suppose this H is span of functions f of x of x. Meaning it's functions of x, but they all depend on x through some big X. Which is the same, more or less, as span, well, provided the measure is good enough, polynomials of x of x. Then P is the condition of expectation. With respect to x. Make sense?
Sorry, can you say what P was orthogonal to? You say it's orthogonal projector, and you give the definition of the inner product at the bottom. What am I looking at?
You want explicit form of P.
Well,
I can do that. It's not a big deal. So you can erase this part. So let's.
I think it's orthogonal. This is the subspace, and this is the projection.
P is self-adjoint with respect to the inner product.
Yes, P will be self-adjoint with respect to the product. So basically, suppose you have basis in. Suppose you have H, the span of, let me call them F0, F1, Fn, etc. Could be infinite, could be finite. And let me pick these guys to be orthonormal. Meaning that if I take, now I'll use physicist notation entirely, right, Fi fj, which is slightly more mathematical notation, fj, and the definition integral fi of x fj of x, rho equilibrium of x, dx is equal to delta ij. So this means that equilibrium correlation functions vanish, right, of these quantities. So these guys are the span, so then P you can more or less write like this, right? So P is just the sum of K, which is usually written as this, right? Fi, meaning if you act with P on some f of x, this will be sum over K, then we'll have coefficients fi f fi. So and if we write this explicitly in terms of integrals, will be integral f of x, fi of x, rho equilibrium of x. That's my coefficient, and then I'll have fi of x. And so that's sort of the explicit form. Now in theory, yeah, I'm way behind my time. So in mathematics, very often, especially when people deal with stochastic processes, this type of expansions are known as polynomial chaos expansions. So if you have your measure, some Gaussian measure generated by a stochastic process, this Rho equilibrium, then you'll get polynomials of, say, Brownian motion will be the basis in your observables. Now, if you take, so let me explain how this works. This part, so this part requires a bit of thinking in a certain way to understand why this is so. So suppose you take a function x, quantities depending on little x. Now, suppose how do you create this conditional expectation? Conditional expectation is just L2 projection with respect to your probability measure. It's nothing more than that, right? Because if you have conditional expectation, a function f of x, conditional on x, this is some function of tilde of x. And then if you take it one more time, it doesn't change. So in reality, conditional expectation is exactly a projection operator in the L2 space of the probability space, right? In your probability space is your Hilbert space here with Rho equilibrium as a measure. Now, but think about this. So this projection is a projection on functions of x, and functions of x can be, generally speaking, represented as polynomials of x with various coefficients, right? You can formally expand it in Taylor series. So if your measure is such that it allows for a complete basis in L2, then you can take any function of x and expand it in terms of various, well, polynomials, orthogonal polynomials with respect to that measure. So in other words, conditional expectation is a projection on the entire span of polynomials of x. But you don't have to project on this infinite dimensional space, right? You can project on a finite dimensional space, just on a set of few select functions. It's also possible. Yes? Yes.
Can I ask a
Yes.
question? Is that K there in the sum, in the projection operator, it doesn't go over the whole set, otherwise you would get the identity, wouldn't it? You're only projecting on part of it.
No, this is H span, so I'm not making a basis in the entire
So
L2. I'm only
that's-
making basis in H, in my subspace, which I like.
So that's a complete set of function.
Complete in
It's
H.
not complete.
Yeah, so this will be
Otherwise you would get the identity first.
where?
What?
It is identity. The projection operator is identity in the space where it acts. It's identity in its range always,
Okay,
right?
okay, so that's fine. Yes, within
So-
its- yes.
Within its range, it is an identity. There's no difference. So
Sure. But if I see it over the
yeah,
two
yeah.
things, that would only be.
That's why I wrote H a span of this, not the L is the span of
So
this.
could you write the total function as sort of product of the f and some other unknown function, and then you would only be.
Yes, so you can represent, say, take H orthogonal
Exactly.
and call this span of,
Yeah.
let's call them G naught And then the identity will be the entire sum of f's and g's in the entire space. And then when we're acting with p on f, then you can take f and write it sum over
That's
f's i's plus sum gi's.
yes.
And all this will be killed by the projection, yeah. Yes.
I mean, so talking out the tree, but all the properties are related to little x. You have an invariant measure with respect to little x.
Yes.
But you're doing all these projections, in a sense, in terms of big X.
Yes.
So can you transfer the properties that you have on little x to big X?
Well, you see, little x, you can forget about little x right now, in a sense, because little x, you have initially an evolution in the space of little x. That creates you a density. The only thing I care at this point is this rho equilibrium. It's certain invariant measure for that process. But from the sense, when I go to the function space, I don't really care about the process anymore. All I care right now is the existence of measure on my space of observables. And I simply average with respect to this measure and call this an inner product. So I introduced a Hilbert space, which is just a L2 space with given measure. So right now there is no relation to the actual dynamics. So it will sort of show up because important property is that L is going to be antisymmetric with respect to this in this L2 space. Or if you have IL, it's going to be Hermitian.
So in essence, you need to have a zero eigenvalue of that equation, and the row back will be the eigenvector corresponding to that.
Yes. So if you look at this equation, that's exactly what it
basically
says.
the
Yes,
same.
that's your invariant measure. Well, I mean, you can have, if you have a single consort quantity like a Hamiltonian, you can take any function of your Hamiltonian, actually. It's going to be an invariant function. Generally speaking, the reason people use Gibbs measure is a different story altogether, right? But formalism doesn't, the general formalism doesn't change. You can have microcanonical if you want here. You can have another function of Hamiltonian. They will all satisfy invariance property, and rho will always, the operator L is going to be antisymmetric with respect to it, and that's the important part.
Right. But the point is, I mean, I think to address Gianpaolo's question, the point is that I started to do my dynamics on some x's.
Yes.
But it's going to turn out that in writing down my equations, there are some other variables that are going to be important,
Yes.
right? And in principle, they're all important, all of them, right?
Yes.
But in practice, that would be far too many. And
Yes.
so I'm going to try at a later stage to choose some macroscopic variables or slow-moving variables or something.
That's
Right? But
correct.
at the moment,
Yes.
right, I don't know what they are, and in general, if I go to a different problem, they're going to be a different set. And that's what you mean by interesting quantities.
Yes.
There are some other macroscopic variables that are going to be important that I want to concentrate on.
That is true.
Yeah.
That is true. Possibly, well, here I'm just decomposing an equation. In the end, once we have a decomposition, we're free to choose our space, whichever satisfies our needs. So we can put all the interesting quantities in our space, stuff like that. I have 10 minutes to do all that. So
Study the whole of physics.
maybe I should start convincing Mike to give me more time at some later time.
Well, no, you're welcome to, but it's not me you have to convince.
Okay.
So the seminar organisers are...
I'll have to convince the audience to write a letter to our
I think it's
department
John
head.
Ball.
John Ball is
Yes.
sort of nominee.
And he's so easily convincible.
Especially he's not here, right? So you don't have to start with all this. Okay, so you get this. So that's the idea. So you do some projection operator, and you go back to those things, and you can express now the first term in certain way. So let me actually, it's good that I've written down the part with h is span of something, so I'll actually write my projection operator right away as sum over k, fk, fk. And of course I'm abusing notation again. I have that f of x, which is an arbitrary function, and fk's are my basis functions in H.
So, Ibrahim, the thing you actually chose was capital X as a function of little x.
Yes.
That was the first thing I chose, and then from that followed H, and then from H followed the F's, which are the orthonormal basis.
Yes. So in principle, like easy choice, Fk is kth order orthogonalized polynomial of x. So that would be the kind of classical polynomial chaos representation in stochastic processes.
But if I was being completely explicit, I also would want to know what capital X was as a function of all the little x's.
Yes, that supposedly is given to you. That's a
Okay,
quantity of
right.
interest and you know what it is.
Okay,
So it's a
fine.
certain phase function which you know what it is. Now, okay, that equation is equation for any of my f's. Any f can be there. So let's do the following. So I start with these basis functions and I'll track the entire subspace as it evolves. So I'll track the subspace of my basis functions. Instead of fk is initial function, I'll start tracking it and I'll write fk of t. That's your Heisenberg representation if you want, right? So if you want to track the functions on the phase space as it evolves. So I can write an evolution equation for the fk itself, looking at it as a function, right? So I'll write fk dot, now I'll have a function of t here. Writing what it is, so I have fk fk L and fk. There's no t's here, right? There's all of those things, they are in my frame which is not rotated yet.
Are you assuming that this H is invariant under the?
No, it's not invariant, it's going to move, so the entire thing is going to move. So, let's see what do we have here. We have e to lt acting on fk, which gives me fk of t.
Sorry, why is there no contribution from Q?
Yeah, there is, that's why I'm writing this plus. I'm just working with the first term only. So it's... So we can write this explicitly, right, if you want.
Another thing, is the K the same on the left-hand side or the same as the K in the sum?
Of course it's not, so it should be, this should be J. Should be J. It's a good comment, because otherwise I'm not getting the quantity I want.
Yeah.
Sorry. I, and this is JK, yeah. Sorry, yeah. So this thing has a certain name in physics, and of course...
What is H?
L.
It's an L.
L, that's my L.
That's an
That's
L,
my
just curls too much.
curly L.
No, flatten the face.
So this is usually called omega kj. It's so-called frequency matrix. So you see, we finished the first part. So we finished the part which now contains the basis in our interesting subspace evolving in time, and this only depends on that basis. So there's nothing else. We have functions fk of t here, the functions of the same functions on the other side, and this matrix, the frequency matrix, is given by equilibrium correlation functions, right? We have omega kj is integral of fj of x, L acting on fk of x, integrated with rho equilibrium of x dx. So that's the formula for my frequency matrix. It just contains, basically, right, inner product of force acting, equilibrium force acting on the kth basis vectors and jth basis vector. Now, here is a trick. So this actually, if L is antisymmetric, then the dynamics is orthogonal, right? If you have L antisymmetric operator, E2 minus LT is orthogonal. So if, let me write it here, if L is antisymmetric, well, it has to be like kind of anti-self adjoint, but if it says antisymmetric, then essentially anti-self adjoint, so for proper kind of mathematical term, then e to power LT is orthogonal. And in fact, you can have this identity, right? Fj L Fk is of course then equal to Fj of t L Fk of t. Right? So the reason I'm not putting proper inner product sign, because you can put it anywhere here. L is going to be, well, if you can throw L there, you'll get a minus sign, but because you can write like this, okay, e to power LT Fj L e to power LT Fj, right? And if it's orthogonal dynamics, you can just forget it. Doesn't matter. Yes? It's orthogonal in the L2 space. So you can compute these quantities either in the moving frame or in the original frame. That's the point. So these quantities can be computed in the sort of in the originally or in the end. Okay. I'm terribly out of time, so what we're going to do about that? I need to derive the second term. Can you suffer through?
Just carry on.
2 minutes?
You're not yet out of time.
Okay. Not yet out of time. Good. So any questions here? Does this make? So the frequency matrix is...
In the second line, that's 1 over k, is it over j?
Yeah, this sum should be over j. I didn't fix that. Thank you.
Looking back to your example on Wednesday, you didn't have this term because you just had one variable in your...
It just
particle
happens to be
equation.
0. Yeah, that term happens to be 0.
Yeah. So all the other terms we're going to see are going to
Yeah.
be similar to
Yeah.
terms that appeared on Wednesday.
So here is, okay, one more comment before I go to that, to run out of time entirely. This actually is again a condition of expectation in hidden form. So look at this. This is actually very important because there are some people who are doing all this using conditional expectations and some people who do it sort of using this linear framework. But these are the same. There's no difference between the two. So suppose again, let's go back to the situation where Fk is the polynomial of kth order of x. The kth order polynomial. This is a linear equation, right? There is nothing nonlinear about it. It just tells me that I have pk dot is equal to sum j, and then I have certain omega kj, and then I have pj here, right? As a vector. Plus, blah, blah. But, I mean, if you look at the first equation, we'll get x, say, let p1 is equal to x, maybe. p1 dot is equal simply to x dot of t. It will be sum over j, omega, and then I have, my k is 1j, and then I'll have, well, polynomial j of x. Right, now this is exactly a conditional expectation of actually Lx. Conditional back on x. Nothing else. Right. So if you look, this is you're looking at the operator L projected onto your action of the operator L projected onto your subspace. And this is exactly a projection of your generator, of the generator of your dynamics on the subspace spanned by all possible functions of x. So it's nothing else but expectation of Lx back on x, right? Because if you have big dynamical equations for x, of course, Lx is not just a function of big X, it can be there's all the other degrees of freedom which you killed. But projection average them with respect to equilibrium measure, so in other words, it's exactly the conditional expectation. So in particular, you can see if you start with the Hamiltonian dynamics and select a few conjugate variables, this term, the first term with the frequency matrix, will be exactly the same Hamiltonian dynamics with your free energy, with the effective Hamiltonian. So if you had, say, P dot is equal to dH of big, so Q dot. I think it's more important to finish with this than to go to the next. So P Q, little p, the big P, P dot is equal to minus dH dq. Again, so take the Hamiltonian system of this sort, and now you want to kill this and write generalized Langevin equations for just big P and big Q. So what you will see that when you write down the equations for so the P part, this projected part, so you're going to get the conditional expectation, and of course the conditional expectation, say here, what is the, so we have my Liouville operator acting, say, on Q is the HDP, so you're going to be averaging the HDP, so L Q condition on P and Q is simply going to be dH dP, right? And your conditional expectation is nothing but e to power h minus beta h, if you want to take your equilibrium measure, over integral of e to minus beta h, where you integrate over fast variables. So you need to normalize it. Pq, little q, and here you integrate by little p, little q. Right? So that's I'm just constructing from Gibbs measure, I'm constructing conditional expectation by normalizing, integrating out P and Q.
But you never normalized before, so why do this?
No, this is a conditional expectation. So this is, see, this is conditional on X. So in order for me to condition on big P and big Q, out of this measure I construct a conditional measure, which is just taking the same thing and integrating out the variables for normalization. That's more or less exactly what it is. So you can write it as d dP minus what, 1 over beta logarithm of your integral e to minus beta h, where you integrate dP dq. So that's how the free energy effective Hamiltonian shows up in this formulation. So if your reduced variables are again Hamiltonian variables, conjugate Hamiltonian variables, you'll simply get again this kind of the projection part will just give you the effective Hamiltonian equation from the effective Hamiltonian. Okay, now I'm officially out of time. So can you survive for 10 minutes? I'll at least try the formulation for the remaining terms. Okay.
I think 10 minutes will be okay. We have to remember the lady in there who's doing the technical support.
Yes.
Also needs to go to lunch.
I
don't think 10 minutes
we can
over is
finish
unusual.
the technical support part, and I can keep on writing. So yes, you see, I haven't given this particular lecture, so I'm not sure how to time them properly. That's why. Okay, so now we have the last bit, and that's where we're going to use our variation of constants formula. So we have, let me recollect our variation of constant formula, e to the power at. Let me write it like this, a plus bt. Let me first try the equation like this. X dot is equal ax plus f, and then I write x is equal to e to at plus integral 0 to t e to the power at minus s f of s. So here will be x naught and ds. X of t is my variation of constants formula. So if my if x dot is equal to a plus bx, right, I can write f is equal to bx, and then I'll have x of t is equal to e to the power at plus integral 0 to t e to the power a t minus s. Now f of s is simply bx of s, but bx of s is e to the power a plus bt. bs here, bs. Now I can multiply all of this by x naught. Yes, so that's the abstract version of variation of constants formula, which says e to the power a plus e to the power a t minus s b e to the power a plus ds ds, right? And to complicate things even further, I'll just transpose this equation. I'll write e to the power a plus bt e to the power at plus integral 0 to t e to the power a plus b s b e to the power a minus s ds. So how do I get from here to there? These are just transposed equations. If you think, you take transposition of this equation and then remove the transposition sign. So I'll get transpose, 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 and then just crash them, right? Because I change the order when I transpose. So this will go front, this will go back. And then I'll just erase these t's, and I get my formula. This formula is a bit too. So this is the same. Suppose you solve this equation, but not acting on the right, but acting on the left. And then your integration by this variation of constants formula, integrating factor formula, will just have this form from the beginning. So it's just somehow, for me, it's more natural to derive it this way and then transpose. So that's the formula which we're going to be using. And here I have e to the power lt, which is e to the power qlt plus plt. This is going to be my a. This is going to be my b. So what do I get? So I'll get e to the power lt, and then I have ql f of x is going to be equal to, so e to at, e to the power qlt, and then I'll have again qlf plus integral 0 to t, okay, e to the power ls, well, b, what's my b? B is my pl, right, and then I have e to the power ql t minus s, and then I have my ql f of x. Just some transformations. And we're almost finished. So this is what's called the generalized Langevin force. So you see, this is the propagator. So let me call it W of t, maybe with dot, is equal to e to the power QL t QL f of x. Then QL you can put here if you want, they commute, right? So what are we looking here at? So at time t equals 0, this is just the action of all other degrees of freedom on the rack, right? So what you're looking at, Q is the projection on the orthogonal plane. So PL gives you action of F on itself, and then QL gives you action of everything else on F. And now you propagate it, but you propagate it with the dynamics, which is called orthogonal dynamics. And the reason it's called orthogonal dynamics because it's generated by QL, which means it's going to be orthogonal to anything which lies in the P space. If originally there was no component in the H, in that space spanned by where P is identity, so then this will be orthogonal to that always. Okay, generalized Langevin force. So the only thing I'm left with now is to do the generalized fluctuation dissipation theorem, and that's, I think, the place to finish. So I have to complete these equations, right? So I have these equations, now I have to go back here and fill in these dots. So let's fill in the dots. So I'm going to put here first, well, my generalized Langevin force. And now the generalized Langevin force, let me now put the index here corresponding to Fk, right? So I had equation for Fk, and I'll have omega k dot of t. So k meaning it's force acting on Fk. And then I'll have plus integral from 0 to t, well, e to the power ls pl right, I'm putting again my p as the projection operator, l e to the power ql t minus s QLF Fk ds. So now we'll pull out something which is called the memory matrix, and let me try not to make a mistake. So integral from 0 to t sum j equals 1 to infinity. Let's see, I have my vector fj in the end, and what is the matrix? So this e to the power ls will give me fj of t. I'll just leave it there afterwards. I have this matrix here, fj l e to the power ql t minus s ql fk acting on fj of t. S, sorry. So this is s. S. Now this is what we call memory matrix. Let me put it as, I don't know, M. Kj.
You still have the Langevin force?
Hmm?
Do you still have the Langevin?
Yes, plus the Langevin force. So it means this plus W k here. W dot k t plus. Now the interesting part is that this satisfies the fluctuation dissipation theorem. And here how it looks. Look at this thing. I have fj, l, ql, fk. Now, suppose L is anti-symmetric. You need anti-symmetry for fluctuation dissipation theorem, otherwise you don't have it. Then I can take this L, right, and throw it to the other side. So I'll have this thing is equal to minus L Fj e to power QL T minus S QL Fk. Now, let's go further. QL and QL here, they commute. So you can take this and put them before the exponential function. Let's go further. If L is antisymmetric, now, and ρ is the equilibrium measure, then Q is going to be a symmetric operator, and P is going to be a symmetric operator also. The projection operators, right, which are projection operators in L2 of ρ, they are going to be Hermitian operators with respect to in L2 of that invariant measure. So in other words, I can throw Q on the other side. Okay, let me carry out everything slowly. LF, I'll put here Q, and I'll put again Q, e to power QL T minus S QL Fk. So what did I do? This is my projection operator, right? So I can just double it, so nothing hurts me and prevents me from doing this. And then I'll take this part and I'll throw it on the other side. So this is going to be minus QLF. Okay, I'm losing my curly scripts when I'm going fast. QLF. And then I can kind of reshuffle things back. There's no QL anymore. I just commuted it. E to power QL T minus S QL Fk. And this is J, this is J. So what do we see here? Here we see that MKJ, this is my W at time 0, W dot, this is my W dot at time T minus S. So MKJ, it's a function of T actually, so I should write here as a function of T. T minus S is exactly W dot 0, W dot T minus S. So that's the that's what's called the fluctuation dissipation theorem.
Sorry, with the minus sign.
Yes, with the minus. Well, usually M is defined with the minus sign to get. Let's put minus sign here and no sign here. This will be minus signs, but M will have no minus sign. I'll define this as minus MKJ. Because, okay, I'm making a very bad board work now. Everything is a big mess. So let me just write the final expression for everything, and we can have a final discussion where we can write equations here. Bad color. Write them like this. So Fk dot is equal to sum over J omega Kj Fj minus integral 0 to T sum over J Mkj of T minus S Fj of S ds plus W dot of T. So that's the generalized Langevin equation. And let me repeat definitions of omegas and m's. So omega kj is fj L fk. MKJ.
Do you have a K and the W somewhere?
Hmm?
Do you have a K and the W?
WK, yes. I was putting it up there. MKJ is equal to expectation. So I need to have T. Hmm?
The bottom left of that column.
Bottom left.
Yeah.
Here?
It's in yellow at the bottom of
Yeah, okay. F omega top omega dot. So let me put here whatever T, S, whatever you want. I'll put T here. Omega dot of T. And then omega itself satisfies the orthogonal dynamics equation. So omega dot of T is e to power QL omega dot T. Not QL, it's just QL. I put double dot ddt. Need to put double dots. The omega dot of 0 is equal to QL K FK. Right, of K. 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 Okay, so that's I
In
think,
the M line.
Yes.
Definition of M
Yeah,
WK and
K and J.
WJ.
okay, too many people talking at the same time.
We're all saying the same thing.
We also did.
Incoherently.
In the MKJT line,
Uh-huh.
you need
Memory
the
of
initials
Yes,
on the
okay,
K,
no, there's no
and
J.
J,
So
and
there's KJ, that will be JK here. So this the
It
change
was an
order.
upper one before, but it's okay. It's clear.
Okay.
So that's the sort of formalism. Okay, there's no real job, right? This is just a big piece of mathematics which does not lead much to anywhere, and unless you do some physical or something.
3 hours in.
But we're going to have to stop now, I think,
Yes.
because not only
Okay.
do we have to go to lunch, but she also has to lock
Yes,
up the room.
yes, yes.
So
Yeah, thank you for your
Thank
attention.
we should perhaps put a little to be continued on the book.
Yeah, I guess so. I should.
Please leave.
Okay.